Hello, welcome back to A Slice of Physics. In this video, we're going to explore the concept of the electric field. We're going to first discuss what the electric field is and talk about things like is it a vector or a scalar, how is it measured, what are its units, and then we will see what the electric field is like near a point charge. As we move around the charge, how does the electric field change? Then we will relate the electric field to the concept that we have already discussed, which is the electric force. We will see how the electric field influences a charge that's placed in a location with a specific field. Let's start our discussion with something we're already familiar with. We got two charges over here, and we want to evaluate the force that charge Q1 applies on charge Q2. And for the purpose of example, let's just say that the charge Q1 is positive and charge Q2 is also positive. Well, the first thing we know is that like charges repel, so the force on Q2 would be directly away from Q1. So the force of 1 on 2 would point like that. And we have also discussed in previous videos the magnitude of this force. That's given by this Coulomb constant K times the absolute value of charge Q1 times the absolute value of charge Q2 divided by the square of the distance between them. So this distance over here is r. One other thing we mentioned is that this electrostatic force of one charge on another, is a long-range force. The charges don't have to be touching each other in order to apply a force. They can do it over a distance, in this case r. Okay, that was all a quick review, but now let's move on to talking about electric field. Well, if the charge Q1 applies a force on charge Q2 at a distance, how does it do that? What if I don't even have charge Q2 and I only have charge Q1? So let me reproduce that over here. Here's Q1 and here's the location in space where I want to place Q2. I haven't placed it yet. It's just a location in space near Q1 at a distance r from it. So I've taken the same situation that we had before, except I've taken charge Q2 out of there and there's only one charge. The question is, does this single charge somehow affect this location near it, or for that matter, all locations near it? And the answer is yes. The way in which the charge affects the location near it is called the electric field. So just a single charge at a distance modifies the space around it and creates something called the electric field in the region around it. And the second part of the story is that if there is a point in space with an electric field, let's not worry about where that field came from. If I place a charge in a location that has an electric field, that charge will feel a force from that field. So essentially all we have done is taken the old example of two charges applying forces on each other and separated them to say that a charge changes the space around it in creating an electric field around it. And when you place another charge in a region of an electric field, that field applies a force on that charge. Okay, so let's now discuss what this electric field is. The electric field is a vector. That's the first thing about it. So it also has magnitude and direction, just like electric force does. The magnitude of it is given by an equation. The electric field is K times Q1 in this case. Let's say I'm talking about the electric field of charge Q1. So it'll be the Coulomb constant K times the absolute value of the charge Q1 divided by the distance of the point at which I want to know the electric field squared. So it looks similar to this equation of force, except the fact that it only focuses on the one charge since I don't have the second charge anymore. Let's study this a little bit more. So this equation tells us that if the charge is bigger, so let's say instead of a 1 Coulomb charge, if I had a 5 Coulomb charge, the field around it would be 5 times stronger. The electric field is directly proportional to the magnitude of the charge that we are measuring the field around. The second thing is it's inversely proportional. Our distance is at the bottom, so it's inversely proportional to the square of the distance. So if I move twice as far away from this charge, so instead of being at the distance of r, if I'm at the distance of 2r somewhere over here, the field would be smaller, and not only will it be 1/2, but in fact it would be 1/4, twice the distance, squared will give me a factor of 1/4, and that's how the magnitude of the field would change, same as how the electric force changed with separation distance between the charges. Next, let's see what the units of the electric field would be. So if I just look at the units on this right-hand side, the unit of K, Coulomb constant, was Newton meter squared per Coulomb squared. You'll remember that from our previous discussions. I multiply that by a unit of charge, which is Coulomb, divide that by a unit of distance squared, which is meter squared. This meter squared cancels this meter squared. This Coulomb cancels one of the Coulombs over here, and that results in a unit of Newton per Coulomb. And that is, in fact, the unit of electric field. Later, we will see that another unit of electric field is volt per meter, but we haven't introduced volts yet, so let's save that for later. So this is the SI unit of electric field, Newton per Coulomb, or as we will see later, volts per meter. Okay, all that is about the magnitude of the electric field. Let's see what happens to the direction of the electric field. Because it's a vector, electric field has direction in addition to magnitude. And here's the simple rule for direction. If the charge is a positive charge, the electric field points away from it. So points away from positive charge, and it points towards a negative charge. So if I have a positive charge over here, the electric field at this point would point away from the positive charge. If I move farther away to about twice the distance, the electric field would still point away from the charge, but only be 1/4 as strong. Doubling the distance will reduce the electric field by a factor of 4. And if I'm over here, it still points away from the positive charge, so it'll point like that. If I'm over here, it'll point away from the positive charge, so like that, and so on. And instead of the positive charge, if I had a negative charge, let me take that over here, and I want to know the electric field at this point, it would point toward the negative charge. If I move twice as far away, it'll still point towards the negative charge, but be 1/4 of what it was before. And if I choose other points, again, it'll point toward the negative charge. And finally, to tie the story in, we said if I now place a charge in a region of space that has an electric field. So let's say in this region of space, I have a point over here, and it has an electric field. I don't care where that electric field came from. There is an electric field in this region of space. Presumably came from another charge like Q1, but let's not worry about that right now. If there is an electric field at a point, and then I place another charge at that point, so in this case, let's say I put charge Q2 over there, what would happen? Well, the electric field will apply an electric force on a charge. That's what it does. So in this case, if I want to get F2 from the electric field, force from the electric field on charge 2, that would be simply the charge Q2 times the electric field that's in that location. To write this equation fully correctly, I got to remind myself that force is a vector, and so is electric field. Charge is not a vector, it's just a scalar, so Q is just left like that. So now as we look at this equation, we can remind ourselves that the charge itself can be either positive or negative. And if it is a positive number, when you multiply any vector by a positive scalar, you do not change the direction. So this tells us that if my charge Q is positive, then F and E have same directions. But if Q is negative, then F and E have opposite directions. So this equation works really well while we take the sign of the charge into account. So we don't just take the absolute value. The sign of the charge helps us figure out the direction of the force and how that's related to the direction of the electric field. So all that's good. And I also want to point out that if we just take the scalar form of this equation, so I got F2 equals the absolute value of Q2 times E. I'm now removing all sense of direction from this equation. And then if the electric field came from charge Q1, I can use that equation over there. So this is Q2 times K times Q1 over R squared, which you can see goes back to this exact same form. So all of this ties in very nicely. We took the concept of the electric force between two charges and split that into the electric field that's created by just one charge and the force that that field applies when another charge is placed there. Let's test these conditions based on these examples that we just took. So there is a field at this point near a positive charge that points away from it. What happens if I place another positive charge over here? Well, we just saw that if I place a positive charge, the force on it from the field would be in the same direction as the field. So the force it would feel would be in that same direction. And that makes sense. Two positive charges will repel each other, and so that works. Now, instead of a positive charge, if I took a negative charge and placed a negative charge at this point, now this equation tells us that because the charge is negative, the direction of the electric field and the direction of forces are opposite each other. So the direction of force would act like that, which again makes sense. I've got a negative charge near a positive charge. That would be an attractive force, so that direction makes sense. And you can test putting a positive or a negative charge near a negative charge, and you will see that all of those conditions work as well. So in this slice of physics, we explored the concept of the electric field. First, we realized that the electric field is nothing but the influence of a charge or a set of charges on the space around the charge or charges. Then we said that the electric field is a vector, so it's got magnitude and direction. As we explored the magnitude, we saw the equation told us that it's directly proportional to the strength of the charge. Higher the charge, stronger the field around it. And it's stronger closer to the charge and weaker as you move away and falls off according to this 1/r squared relationship. As far as the direction goes, we said that the electric field points away from a positive charge and towards a negative charge. And then we discussed the units of the electric field, which is Newton per Coulomb in SI units, or another way to specify that is volts per meter, as we will see later. And we close the loop between force and field by reminding ourselves that any electric field applies a force on a charge that's placed at a point with the electric field. Thanks for watching. I'll see you soon.